Ludwig, which is an open source project that I created and I'm the main maintainer of. And because we recently added some new AutoML features, I'm really happy to talk about them for the first time here. So what is Ludwig to begin with? It's a code-free deep learning toolbox, which basically means that to use it, you don't really need to know how to code. You can just provide a really simple configuration. We're gonna see how to do that in the course of this presentation. And it is based on TensorFlow, which basically means that all the models that you will be training will end up being TensorFlow models, so you can then use them the way you want. And these statistics are a little bit outdated now. Things are even better. We reached almost 7,000 stars right now, and there's many contributors and many commits per month. So it's a really active project that has been developed in the last year, basically. And these are a set of companies that use Ludwig and a set of institutions that support it. In terms of architecture, what I tried to create with Ludwig is a tool that, first of all, was had to be general. So I created this data type abstraction that I'm going to tell you about in detail. And the idea is that allows this toolbox to be used for many different machine learning use cases. Also, I tried to make it as flexible as possible in order to allow both unexperienced users and also experienced users to have obtain some value from using Ludwig. I also tried to make it extensible. The reason is that every day there's a new deep learning model that comes out that is more accurate than the previous one, and so making it extensible allows it to keep the pace with the current research. Another focus of Ludwig was understandability. Deep learning models are kind of a black box, and despite the fact that there are some techniques that allow to inject some explainability in them, what I've tried to do with Ludwig is to provide some visualizations that can give a glance at both the performance of the model, but also the predictions of the model, and also to compare different models. I also tried to make it as easy as possible to use, and I will show you both examples of really simple command line interface to use it, and also some programmatic interface to use it later on. Finally, it's open source, it's Apache licensed too, so you're really welcome to use it, hack it, change it, submit PRs, submit issues, and get involved in the community. So let's start with a really simple example that is basically Ludwig in a nutshell. Assuming that you have some data that looks like this. This is a table where you have two columns. One is news and one is class. The news column contains some text, and the class column contains some categories. And so what you want to do is you want to train a model that, given a new piece of news, can predict a class. This is all you have to do with Ludwig in order to train such a model. You have to use the command Ludwig experiment, provide the data, in this case as a CSV, and then provide the model definition, which is the real core of what Ludwig does. It's a declarative structure that allows you to define the model, basically in terms of the inputs that it's gonna take care of, and the outputs, the predictions that you want to obtain from the model. In this case, you can see that the model definition is a dictionary with two values, input features and output features, and the two keys, sorry, and the values associated with those input and output features are lists. So you can use more than one input feature and predict more than one output feature at the same time. And those lists contain information about the features, in this case, news of type text, and the output is class of type category. In some cases, these model definitions could become a little bit bigger than this, and you can provide them as a separate file, as a YAML file. What happens when you call this command is that what you obtain is a training process. So Ludwig trains a model first by doing a split on training, validation, and test, but you can also provide your own splits. The model is trained on the training set by validating on the validation set, and then predictions are obtained on the test set, and performance is evaluated on the test set. So this is what happens after the first epoch. As you can see, there's like a bunch of metrics and that are computed at the end of the epoch on all the splits. After a few epochs, the validation accuracy improves, and so the models are saved. and then after a while, the validation accuracy doesn't improve anymore, and so there's some early stopping. The model with the best validation accuracy is then used for obtaining predictions and for evaluating all the different measures. And there are some test statistics that are over all the data set and over all the classes, like these ones that you can see here, accuracy is at K, the confusion metrics, and a bunch of other metrics. But there's also some class-specific metrics, like this one, it is specific for the class earn. And you can see that there's all sorts of values that you obtain from here. So this is basically Ludwig in a nutshell. Now let's look at how it works more under the hood. There's a training procedure that works like this. It's a really simple kind of standard way to do training. There's some raw data and there's some pre-processing that is performed. During pre-processing, some feature mappings are obtained, which are then used also at test time for mapping features in the same way. For instance, one mapping could be mapping a class to an integer, and so you want to do the same mapping also at test time. Pre-processed data is then provided to the model training that saves the weights and the upper parameters of the model. At prediction time, new data is mapped and pre-processed using the same feature mappings obtained at training time. Pre-processed data is then provided to a model that is loaded from the weights and the upper parameters obtained at training time, and some predictions and scores are obtained from the model. Those are mapped back into data space using the same mappings that were obtained during training. For instance, the model can predict class number 10, and then because of the mappings, we know the class number 10 corresponds to like sports or something like that. The experiment command that I showed you before basically performs first the training and then the predict, and saves all these weights, upper parameters, and feature mappings, but at the same time also provides final predictions and training and test statistics. These objects can be provided then to a visualization component that allows you to obtain some graphs and visualizations, and I will show you some examples of that later. Right, so what happens under the hood when you try to train a model with Ludwig? The magic lies in three different things. First of all, the data type abstraction, and I will show you some examples of that. Second, the declarative model definition that I already show you one little example of. And finally, there's a smart use of kvargs. If you're familiar with Python, kvargs is a way to provide a function with named key values of parameters. And this allows the user to provide all the parameters of the model in the model definition without, and these parameters percolate all the way through the code to the specific class that implements a specific model. And you will see also an example of that. So going back to our example, this is the part that we care mostly about. It's the model definition. And what happens when you provide this model definition is that it overrides some defaults. And this is the overridden defaults, which looks like a lot of stuff, but let me go through it little by little, and you will see that there's a lot of flexibility that you get from this kind of approach. This model definition is basically divided in 5 different sections. We have seen an example of input and output features, but there's also a combiner that we'll tell you about in a moment, and also some parameters for training and for pre-processing that you can modify as much as you want. First of all, let's look at why you actually need these inputs, combiners, and outputs. The basic idea of Ludwig is that the data that you're providing is associated with some data types. And depending on the data type, different encoders and different decoders are used. And combining different data types and different encoders, different data types for outputs and for inputs, basically maps into having different machine learning tasks. So what Ludwig allows you to do is allows you to encode text categories, numerical, binary features, sequence, vectors, sets, bags, images, time series, audio and speech, H3, which is a geospatial indexing method, and also dates, and to predict text categories, numerical, and so on and so on. This is all you can do, but at the one specific instance of this could be, for instance, having text as input and category as output. And that's a text classifier, the example that we've already seen. But you can provide an image as input and text as output, then you have an image capturing system. Or you can have categories, numerical and binary features as inputs and numerical as output, and you have a regression system. Or you can have audio and speech as input and binary as output, and you have a speaker verification system. Or you can have text and images as input and binary, and you have a yes/no visual question answering system. As you can imagine, the combination of these inputs and output features allows you to do many different tasks, Moreover, each input feature, each output feature has different encoders and different decoders, and the user can specify which one they want. For instance, for text, I have at the moment all these encoders, and there are some CNNs, some RNNs, and some transformer models that are available to you. And this is, for instance, the parameters that you can provide in the model definition for using a parallel CNN. You have to specify the name of the feature and the type as we have seen before. But if you want to use explicitly the parallel CNN, you can just specify encoder parallel CNN and the level, which is something that is specific to the text features if you want to have word or character level encoding. All the other parameters in gray that you see here and some parameters that are specific to the parallel CNN, and they're in gray because those are the defaults. You can change any of them if you want, or none of them, depends on your preference. And when I was telling you about KVArgs, as you can see, this is the class that implements the parallel CNN, and the different parameters that you can provide to the class map one-on-one with what you can provide in the model definition. If you have another encoder, for instance, text CNN, or for instance, an RNN, you can see the only thing that you have to do is to change the encoder parameter. And obviously, this will have different sets of hyperparameters for you to play around with that can be changed again by just changing one string in your configuration. This kind of architecture is really useful because it allows you to reuse code. And in this case, I can use the same encoders for sequences, time series, audio and speech, and so on. While for images, I'm using different encoders. In the text CNN, that looks like BGG and the ResNet, which are pretty standard encoders. And then there's also two different encoders for numerical and binary features, category features, sets and bags, data and H3, and vector features. So you have all these sort of different data types that you can use as inputs. What happens when you have more than one input feature? Well, what you can do is, by default, Ludwig has this concept of combiners, which is a way to take all the information from the different input features, combine them somehow, and provide one output for the decoders to generate some output. The most simple combiner that Ludwig allows you to use, and also the default one, is this concat combiner. What it does is it takes the hidden representations of all the input features, combines them by concatenating them, and then uses some fully connected layers for mapping them into a smaller space. And you can change all the parameters of this. Ludwig also comes with a few more combiners that are more specific for sequential data, but I will not talk about them in this presentation. Then when you have output features, basically each type of output feature defines a different task. For numerical output feature, what you actually end up doing is some regression task. And what happens is that you just project the hidden representation to the dimension of 1, and you can change the loss, you can change the number of the layers of this projection, and so on. You have all sorts of parameters to play around with. When instead you use a binary output feature, the only difference is that you also do a sigmoid on top of the projection, and you can use different losses, obviously, losses that are more clearly useful for binary features, like for instance, using cross entropy. And you can also set a threshold to the level that you want for the final discretization into the binary values. Category features are useful for performing multi-class classification. And in this case, the projection is to n, which is where n is the number of classes, and so the softmax is applied on top. And you also here have a bunch of potential loss options and many other parameters for the loss to play around with. Set features, on the other hand, are used for multi-label classification. And here there's a sigmoid instead of the softmax and a sigmoid cross entropy as loss. Vector features are pretty useful, in particular for use of weak supervision. If you're familiar with that, you can have labels that are probabilistic in nature, and vector features are pretty useful for that. Finally, you can also have sequence features as outputs, and there's two types of decoders that you can use for this, generator and a tagger. The difference is that the tagger assumes that the input is a sequence and produces a sequence of the same length as output, tagging each single element of the input sequence. The generator, on the other hand, is more useful for tasks where the length of the input and length of the output are not extremely related. For instance, when you do machine translation, you don't know if the the target language sentence will have the same length for the input language sentence. And so what happens here is that you do autoregressive kind of generation where you generate one output and then you feed the output back as input for the next step of the generation until you reach an end of sentence token. And that's what you obtain as a generation. There are also many training parameters that you can change here. For instance, you can change the batch size, you can change the number of epochs, the early stopping, which optimizer to use, and all the parameters of the optimizers, the learning rate, and so on and so on. So you have a fully fledged training loop that you can customize as much as you want. And also there's pre-processing. So each different feature, and each different feature type has different pre-processing parameters. For instance, you can change the maximum length of your text or the maximum size of the vocabulary when you are encoding your text. And that is true also for all the other sets of features. So these are all parameters that you can change from the model definition without touching the code. And recently, in terms of preprocessing, I added all these, different tokenizers to Ludwig that allow you to deal with many different texts and many different languages. So this is like an overview of all the things that you can change and modify with Ludwig. Let me show you some example models of what you can actually achieve by using Ludwig. This is the text classification example that we've seen at the beginning. News as input, class as output. And this is all you have to do to train this model. And that's the architecture that you, in the bottom right, it's the architecture that you are actually training. This is an example of object classification where you can use like Hamlin or ImageNet, for instance, as inputs, data sets. And you have to provide the path to the image and the class associated with that image. And in the model definition, all you have to change really is the name of the input, in this case, image path, and the type, in this case, is image instead of text. And you're done. You have an image classification system. Or you can have an speaker verification system where you have two speech files and an output binary value that tells you if those speech files are actually belonging to the same person or not. And so what you have to specify here is two inputs, both of type audio. And for the second input, you have this additional tide weights parameter, which allows you to express the fact that you want to use the same sub part of the model for encoding both speech features. And the output in this case is named same, and it's a binary of type, its type is binary. You can do, for instance, this is similar to a model that I helped developing at Uber when I was working there, which is an expected time of delivery model that takes an input as the restaurant as a category, an order as a bag of items, and the hour and minute where the order is requested, and predicts the ETD, which is the number of minutes that it will take for delivering this order. And as you can see in this case, because there's multiple input features, there's a fully connected layer in the combiner here that was not present in the previous examples. Another possible example, in this case, using a sequence generator, is a chit-chat dialogue model. In this case, you have two users talking to each other, and you encode user one using an RNN, using an LSTM cell type, and you can have an output using a generator decoder that decodes using, again, an LSTM, and in this case, also uses a time. Or you can have tagging of sequences or time series. In this case, it's like tagging of text. You have some utterances, and then you have some tags associated with each element of the input utterance. And all you have to do is to change the decoder from generator to tagger, and then you can obtain this, these kind of predictions from the model. Cool. So hopefully this gave you like an overview of what are the many different options of things that you can do with Ludwig. These are additional goodies that you have for using it from a programmatic API. To install it is very simple. Pip install Ludwig, and the programmatic API allows you to train a deep learning model in 2 lines of code, literally. You just have to import Ludwig model from ludwig.api, initialize an object from the class Ludwig model by providing a model definition, which is the model definition that we've seen before. And then just call train on some train data. You obtain a model that now you can save if you want, and you can also load back with the Ludwig model.load function. And you can also use that model for obtaining predictions on new data. If you want to serve a pre-trained model, you just have to call Ludwig serve and the path to the model that you trained. And it will spawn a REST API that you can query for obtaining the predictions. Right, so I told you about the visualizations. These are some examples of visualizations that you can use that are already baked in Ludwig. The first one is a comparison of different models on different measures. The second one is a calibration plot. The fifth one is a comparison of predictions among two models. So you have about 20 pre-canned visualizations that you just have to provide the outputs of Ludwig to the inputs of these pre-canned visualizations, and it will give you much more insights of what your model is doing. So we're going to release version 0.3 in the next few days, and but many of these, well, the features are already available. So if you go to the master branch of Ludwig, these features are already available in the alpha version or version 0.3. Notably, these are like many different things that we're adding. In particular, we are putting to TensorFlow 2. We have hyperparameter optimization that we'll tell you in a minute. There's new ways to deploy models. We can train models in a distributed way. We have k-fold validation now, and many new things like integration with weights and biases. We already had one with Comet, and also integration with Hugging Face. But let me tell you in detail about the hyperparameter optimization, because I believe it's very easy to use and you can get started right away. So this is an example of an hyperparameter optimization with Ludwig. On the left hand, you have a Ludwig model definition that defines an input utterance and tries to predict a class which is of type category. And the training parameters here are the learning rate, which is 0.001 in this case, and the Adam as an optimizer. And let's assume that we want to optimize hyperparameters, the cell type, the learning rate, and the type of the optimizer. The right-hand side is what you have to declare in your model definition in order to do the hyperparameter optimization. First of all, you predict which you declare which metric you want to optimize for. Let's say we want to optimize for accuracy. Then you specify which parameters you want to optimize. In this case, utterance.cellType, training.learning-rate, and training.optimizer.type. And which are the ranges of the parameters that you want to optimize. For instance, the cell type is a category, and you have RNN, GRU, and LSTM. The learning rate is a float between 0.001 and 0.1 in a log space, and category is used for the optimizer type, and you have SGD, Adam, or AdaGrad, for instance. Once you specify this, then you can have different strategies and different samplers for figuring out different samplers and different executors for actually running the hyperparameter optimization. In this case, you have random grid and PyShot, and we'll tell you in a moment. And the executor could be in parallel serial with fiber. Let's look at these pieces in detail. So what you can specify for obtaining and evaluating your different samples of hyperparameters is which output feature to use. And there could be more than one. So you can, by default is the, if you only specify one, you're good to go. If there's multiple ones, you can specify which one you want to use. And you can also specify which metric associated with this output you want to optimize for. And you can also specify if you want to maximize or minimize the metric. And finally, on which split you want to optimize. By default, it's validation split. For the parameters, you can have different types, int, float, or category. And you can specify the ranges or the different values that can be optimized. For samplers, the moment we have random grid and PyShot. This PyShot optimizer is a Bayesian optimization method, and they have their own parameters. For instance, you can specify how many samples you want, or other parameters for PyShot is like some hyperparameters of the PyShot optimization itself. And for executor, at the moment we have a parallel executor, a serial executor, and a fiber executor. Fiber is like a way to run a parallel computation over a Kubernetes cluster, which is pretty simple to use. And you can specify all parameters like how many workers, if you want to use GPUs or not, and so on and so on. And we are in the process of starting to integrate also Ray and Raytune as executors, and they are coming soon in the next release of Ludwig. And after you run this hyperparameter optimization, there are some hyperparameter optimization specific visualizations that you can do for obtaining additional insights. So you can use the HyPlot library for obtaining this parallel coordinate plot for understanding the results of your optimization. You can also use the graph on the top right, which is a pairwise comparison of all the hyperparameters to see if there's correlation between them. And then for each parameter, you also have this violin plot that shows you the ranges of performance of all the parameters that you care about. Other features that we added is like integrated with Horovod, so you can run your training on parallel in a cluster, and all you have to do is Horovod run the number of workers and this use Horovod parameter. We also added the Hugging Face transformers. So now you can train a Ludwig model by just specifying BERT, DStillBERT, T5, Electra, GPT-2, all the encoders that are provided by Hugging Face transformers. Now you can directly use them out of the box in Ludwig. So basically you can train a BERT classifier without writing a single line of code. You can also add new encoders and new components to Ludwig very, very easily. All you have to do is to create a new class with two methods, init and call. The init method has all the hyperparameters of your new model, and the call just assumes that the inputs are of specific tensor shape and the outputs are of specific tensor shape, and then you can write your own custom code for doing whatever you want, assuming that the inputs and the outputs have those shapes. Yeah, so this is all I wanted to tell you about. I tried to keep it short so that not to steal too much time from your evening, but I'm very happy to answer questions about Ludwig. There's documentation on ludwig.ai that you can look at. There's the repository available for you, a couple blog posts and several videos that introduce Ludwig. And there's also a white paper for the more researchy aspects of Ludwig. And also wanted to thank these key contributors that helped me a lot so far in the development of Ludwig, and I hope that this list will grow even more in the near future. Thank you for your attention.
Great, fantastic. Thanks a lot for the presentation. And I see we have a few questions. If you can click the Q&A and you can go over it from the top.
I have to stop sharing because otherwise I cannot see. Okay, now I can see them. Perfect.
Yeah.
If there's anything that is specific to the slides, I will go back to them. So let me see what are those questions and try to answer them. Is it possible to calculate features automatically within Ludwig, like feature crosses or something like deep learning where we don't declare features directly? So I'm not really sure what you mean by calculate features automatically. In Ludwig, you have to specify at least the columns of your data that have to be used for obtaining the predictions. Then Ludwig creates a deep learning model behind the scenes that encodes them and manipulates them in order to obtain the predictions. So behind the scenes, creating the deep learning model is exactly what Ludwig does. Second question. Sure. Second question. Can you input of different types, text, JPEG, WAV, in the same string to Ludwig, or will it understand the difference and use it? Again, I'm not super sure what you mean by this question. I interpret it as, can you provide a text, an image, and a WAV file all at the same time as inputs to the model? And the answer is yes. In Ludwig, the input features, also the output features, is a list. And so you can have as many inputs of all the different types that you want. And you can create multi-model deep learning models very easily, right out of the box. Great, let me see another question. How can we scale and generate endpoints on cloud? So the training, as I showed you, there is this integration with Horovod, which basically means that if you have a cluster, you can run with Horovod on the cluster using, and Horovod will take care of parallelizing your training in a distributed way, which is very efficient. It's almost linear in the size of the number of machines that you give at disposal. And also, again, the soon to come integration with Ray will make it even simpler for you to train in a distributed setting. And in terms of generate an endpoint on the cloud, so Ludwig provides this Ludwig serve functionality that spawns a REST API using Fast API, which is probably the best thing you can do in Python for serving the models. But there's other HU mechanisms that Ludwig provides at the moment for deploying the models. One is Ludwig can save the model, which basically means that you can use any TensorFlow serving capability for serving the models that you train with Ludwig. Moreover, Ludwig also has an additional integration with a package called the Neuropod, which is a way to package all your model into a really nice and fast inference engine that runs in C++. So it's very, very efficient. And so if you use Neuropod, you can deploy your models at scale very easily. Let me see another question from Janice. Can you share the link to the Ludwig repo? It's github.com/uber/Ludwig. But also, if you go to ludwig.ai, there's all the links that you want. That's the main Ludwig website, and you can find all the links there. Great. Jerison, let's see. Is it possible to add the GUI for Ludwig so that the user can just click on GUI and drag and drop the GUI, similar to Dataiku, etc., so that user can construct pipeline even easier without even write the command like script at all? Yes, definitely. I haven't done it yet because I'm not like UI expert, but I would greatly enjoy having some people from the community to contribute that. I think it would be very, very easy to do that because, again, Ludwig already accepts a YAML file as input for the model configuration. And so a UI that has all this, drag and drop and, drop down menus, etc., that saves the YAML file will be very easy to directly pipe into Ludwig. It will be straightforward and very open to, contributors to helping me out with that because I'm not super, savvy in terms of front end myself. More questions. So how is Ludwig support on DRL? Can all be done by JSON? Not sure what you mean by the DRL. Probably you mean deep reinforcement learning, I guess, if that's what you mean. So at the moment, there are no deep reinforcement learning models and capabilities supported in Ludwig, but it will be relatively straightforward to add new combiners and new losses that would allow for training the deep reinforcement learning models. I guess there's one additional caveat is that one thing that Ludwig does not do is, managing the reinforcement learning environment. So there will be some plumbing that will be needed to be done in order to collect from the environment data and then provide the data as input to Ludwig and the Ludwig predictions as actions in the deep reinforcement learning setting. But there's a relatively easy plumbing that you can do around Ludwig in order to do that. More questions from Janice. Can you deploy models to Internet of Things devices? So at the moment, the models that you have, that you obtain with Ludwig are, again, TensorFlow models. I haven't looked yet into the possibility to make them TensorFlow JS or TensorFlow Lite models. It's something that I will definitely consider in the future. In particular, if there's some, someone with that kind of expertise I want to contribute to it, I will be super happy to accept contributions on that because I don't have direct experience with Internet of Things kind of model, actually, shrinking models to the point that they can be used easily on Internet of Things devices. But I'm very open to the possibility. And if your Internet of Things device is, performant enough to host a TensorFlow model, then you can definitely use it right away already now. Another question, maybe relevant, but just curious, why Ludwig? many, many organizations are Ludwig, seems a popular name. That it's a secret. I will not reveal it in a presentation that ends up on the internet. Sorry about that. But if you're curious, you can reach out to me directly, I will tell you. Paul, for serving, is the code generation or specification to drive TensorFlow serving? I'm not really sure I understand the question, sorry. Let me try. So I believe that what you're thinking is that Ludwig generates code. Ludwig doesn't really generate the code. What it does, it composes the model on the fly, depending on inputs and outputs. And then the model that is saved is, again, a TensorFlow model that is saved that you can then load and use whatever you want. Another question, probably the last one. Is there a feature engineering library that go with Ludwig where I can save the domain-specific feature engineering decision to process data to feed features to Ludwig in production? Not right now, but that's something that I'm gonna explore. And for instance, there is one open PR in the Ludwig repo for doing feature engineering that is specific to time series data, but I'm very, very open to the possibility to add additional integrations to additional libraries for doing more feature engineering